Welcome back to Partial Derivatives in Thermodynamics in Physical Chemistry. My name is Kevin Tokoph. Make sure to like this video and subscribe to the channel for future videos and notifications. It's very much appreciated. Alright, so this video is a little bit, what I would say, out of the ordinary and maybe in some ways out of the realm of physical chemistry. However, what I'm going to show you how to do in this video is something that's very, very, very important for dealing with a lot of equations and things like that in really any branch of physics, advanced chemistry like BChem. All right, so what we're going to do in this is we're going to do substitutions and transformations. All right, so what I'm going to do in this particular video, and we'll do another video another video very similar to this that deals with electrostatics. We're going to deal with everything in this video according to Newton's second law. Force is equal to mass times acceleration. And it turns out that there are a lot of equations that come directly out of this. And I'm going to show you where they come from, so maybe it's useful from a physics perspective. But the main thing to get out of this here is how to rearrange derivatives. Okay, how to rearrange a derivative or a differential equation. Okay, because for instance, if I had an equation like this, and I'll erase this in a minute, let's suppose I had 3/4 is equal to x, okay? Well, what I can do is I can multiply both sides by 4, right? And I can get that 3 is equal to 4x. Okay, that's essentially the same thing we're actually doing here. That's the same thing we're doing. That is the wrong color. That's the exact same thing that we're doing here. Okay, we're just basically treating derivatives as fractions, and we're just rearranging them and making appropriate substitutions to get something physically relevant. Okay, and you're going to be doing a lot of that in physical chemistry. Now, these equations you're not going to be dealing with, but the principle, hopefully seeing a bunch of these, will help you get a feel on how to do derivative and integral and differential substitutions. All right. So force is equal to ma. Let's get started. One thing to realize is acceleration. Acceleration is essentially the derivative of velocity with respect to time. So if you had a function for velocity, you differentiate it with respect to time, and that's acceleration. All right, so all you do is you basically take this a and substitute it with dv dt. All right, that's something you're allowed to do. This is actually the same equation. It's just that acceleration is expressed as its derivative. All right, now, another thing I'm able to do is I'm able to multiply both sides by the same thing. You've done that before. If you had to multiply both sides by 5, you'd multiply f by 5 and this side by 5. But I'm going to do something a little different. I'm going to multiply both sides by dt, right? Now I can do that because I didn't technically change the value of the expression because I multiplied both sides by the same thing. But what that does is it cancels dt on this side. Now what I get essentially, I'm going to put it in differential form first. What I get is f dt is equal to m dv, all right? What this is it's the differential form of the impulse momentum theorem. Okay, so the impulse momentum theorem comes directly out of Newton's second law by doing the simple transformation. So all I'm going to do now is integrate both sides, okay? Because force is a function of time here, so I can multiply by dt, and m is not a function at all, and then this dv is dv. So I'm going to integrate both sides. This is derivative, or the integral with respect to time, so from t1 to t2. This is the differential of velocity, so from velocity 1 to velocity 2. And what I essentially get is the impulse. An impulse is usually given by j for whatever reason, usually because I is the moment of inertia. So j is the impulse, so integral of f dt is equal to the integral of m dv. And a lot of times, usually because you're looking at initial velocity versus final velocity, you're integrating a constant times dv, that is delta v. Okay, so what we say is that the impulse, let me get my box, impulse is equal to mass times change in velocity. Okay, if force was a function of time, maybe it was like t squared minus 3t, then you'd integrate that, and whatever number you get through evaluating the integral is just equal to m delta v. So that's a really simple example, but we can also do different other things to Newton's second law to get some other things out of it. All right, so I'm going to start again with force equals ma, or force equals mdv over dt. All right, one thing I can do right off the get-go is I can multiply both sides by dx. I didn't change the value, I just multiplied both things by the same side. What is f dx? F dx is the differential form of work. Okay, it's the differential form of work. So that means this f dx is dw, and that equals m dv over dt times dx. Now, there is something you're able to do. Let me show you this. I'm just going to use generic variables. dA over dB times dc. Okay? What I'm allowed to do is since I'm dividing by dB and dA, dc is a product, I can move the dB over here and have this dA times dc over dB. Okay? I just moved the 1 over dB to being over dc. All right? So what I'm going to do is I'm actually going to take this dt right here that's in the denominator, and I'm actually going to move it under the dx. All right? So essentially what I have here, I'm going to put it in integral form now. Integral of f dx from x1 to x2, that's just the work, right, is equal to the integral from v1 to v2, right, of m dx dt dv. Why did I do that? Well, dt, put it under dx. I have this dv then that's free now, but notice that what is dx dt? It's the velocity. So now I have velocity and a differential velocity. I can integrate that, right, from v1 to v2. When I do that, I get that work is equal to the integral of v1 to v2 of mv dv. Now, when I integrate this, what do I get? Assuming that v is just the velocity, okay? This is going to be 1/2 m v squared evaluated from v1 to v2. Well, first of all, if I have this, it's 1/2 times v2 squared minus v1 squared. What is that? This is the change in kinetic energy, right? Because notice, what is 1/2 mv squared? That's just a kinetic energy, right? So what did I just show by manipulating Newton's second law this time? That the work is equal to the change in kinetic energy. This is the work kinetic energy theorem. So the work is equal to the change in kinetic energy. So how did I do this thing? I just multiplied both sides by dx and then rearranged the differentials to get what I want. So these are just two things illustrating some rules on how you can manipulate derivatives and differentials within an expression to get exactly what you want. All right, let's do another example over here. All right, so here I have this, I have ultimately right here, I may have actually gotten rid of something I didn't want to. Let me do this. I actually got rid of something. Let me write the m right here. Put the m back right there. Okay, now I have it like I want it. So I'm going to start with what I had over here. F dx is equal to mv dv. All right? Here's what I'm going to do now. I want this to be time dependent. So what I'm going to do is I'm going to divide both sides by dt. Right? That's what I did here. Divided this side by dt, divided this side by dt. Now, these quantities are hopefully things that we know. What is dx dt? Well, dx dt is the velocity. That's this right here. dx dt is the velocity. All right? Now, what is dx dt over here? It's again the velocity. I've just sort of taken v and turned it into dx dt. All right? Now, I'm going to do something a little bit different here. All right? This dt, no matter what, right here, this dt, let me actually do this in a different color like this. This dt right there, no matter what, it's in the denominator. Okay? So I have this dx dt right here, that's just velocity, right? But what if I do this? What if I separate this derivative? So I have this dv right there, and then I just throw this dt under all of it, right? what becomes of that? Well, what is m dx over dt times dv? Well, that's mv dv. That was differential work. We just showed that up here, right? But all of it is still over dt because I separated that out and made it a quotient. So now I substitute this stuff with dw, differential work, and it's over dt. So what is dw over dt? Well, this is power. dw over dt is power. However, I can't neglect what's over here on the left side of the equal sign. So what I have is this expression that force times velocity is the power, which is also the derivative of the work with respect to time. Okay? So that is something that's very, very powerful. That if I want to look at the change in energy or the change in work with respect to time, that's the power, but it's also equal to the force that something collides with something with times the velocity with which it collides. Okay? So hopefully you're starting to see how you can manipulate derivatives. We're going to do also one more, and then we're going to look at an example. Okay? All right. So what if now I want the power to be time dependent? All right? If I want the power to be time dependent, I can actually take this P is equal to dw dt, which is what we have over here. I'm going to differentiate both sides with respect to time. This is something that's a little bit different than what we've done, but you can theoretically differentiate two sides of an expression. You can do that as long as it's with respect to the same variable. Now, one thing that's really important, this is just notation. I could have any function over here, any function, all right? If I want to operate a derivative on this, what I do is I write this in front of it, dx. This is partial derivative notation, but it's still the same thing. If you want to differentiate f, you put this in front of it, d over dx, if it's with respect to x. Okay, and that literally means the derivative of f with respect to x. All right, these are the same thing. So if I want to do this to power, I'm going to multiply this, or at least operate on it, I should say, with this d over dt. That's going to be the derivative of power with respect to time. But I also have to do it on dw dt. So I'm going to multiply again by d over dt. But because you're differentiating something that's already a derivative, that's going to become the second derivative with respect to time. In other words, I'm going to say the derivative of power with respect to time is the second derivative of work with respect to time. All right? And this also itself is a differential equation. It's a second order differential equation. And they're technically, most books don't really teach this particular thing, but this is called a power surge. Okay, and hopefully that makes sense because basically your power is changing. If your power increased from, say, 10 watts per second to 50 watts per second in 5 seconds, then whatever you get by taking the change in power with respect over change in time, that's the power surge. Okay? And it's dp over dt, but that's also the second derivative of work or energy with respect to time. Okay, so hopefully that makes sense. Assume I don't know exactly what the function for power is. I'm not given a function for power, okay? But suppose I wanted to figure out what the power surge was, right? I know that power is equal to force times velocity, all right? So if I want to find out what the power surge is, I can actually do some expansion. So what is the second derivative of work with respect to time? That's the derivative of force times velocity with respect to time. Now here's another rule that you're going to encounter. If you have differential of two variables, a and b, dab, okay? In thermodynamics you'll see dpv a lot because you're dealing with pressure and volume. This differential, you have to use a thing called product rule of differentials. This is going to be a times the differential of b plus b times the differential of a. Okay, this is dab. So if I have dfv, this is going to be f dv plus v df, right? And since it's all over dt, it's going to be f times dv dt plus v times df dt. All right? So the question is, what is this expression equal to? Because this is actually what the derivative of power with respect to time is. What is dv dt? That's the acceleration, right? And F is just F. So I'm going to say this is force times acceleration, right? What is df dt? Well, that's another thing we should probably calculate to see what it is, because normally you don't talk about the derivative of force with respect to time. Let's see what it is. So F, we know that F dt is mdv, right? That's the impulse momentum theorem. What I want to do now is I want to divide both sides by dt, and you'll see why I'm doing this in a minute. Let's divide both sides by dt. That's going to cancel this dv, and I'm going to get essentially, I'm going to get that F is equal to m dv dt. That's just back to Newton's second law. Force is equal to ma. All right? Now what I want to do is, because I'm looking for the derivative of force with respect to time, I'm now going to differentiate both sides with respect to time. That's what we did up here basically with force and velocity. So I'm going to differentiate F with respect to t, and that's actually going to get me the derivative, and that's equal to dma over dt. So what exactly is dma? Well, it's going to be what we did up here. It's going to be m times the differential of a plus a times the differential of m. All right? So this is equal to mdA plus a dm, but we're dividing by dt, so it's mdA over dt plus a dm over dt. All right. Now, there's a simplifying assumption that we're going to make. When we're dealing with we're dealing with usual things that move around. Like, for instance, if I were to throw a baseball, does the baseball change mass? No. When you're dealing normally with normal objects in everyday situations, they're not changing mass. So if you have no change in mass, delta m equals 0, then dm equals 0. So this differential dm dt is 0 because dm is 0. So you don't even have to worry about that. Instead, what we're ultimately going to say is that the partial of f with respect to t holding m constant, because that's technically what this is just df dt, is equal to mass times the derivative of acceleration with respect to time. What is that derivative right there? Well, the derivative of position with respect to time is velocity. The derivative of velocity with respect to time is acceleration. And the derivative of acceleration with respect to time is something called the jerk. And that's given by the symbol just lowercase j. So that means this derivative is equal to mass times jerk. All right? So then what I'm going to do is I'm just going to take this mj and substitute it in for this derivative right there. Right? So now what do I get? Oops, scroll over. So I already had this fa there, that was already determined, but now I can plug in derivative of f with respect to t as mj. So this is going to be, it's going to be m times v times j. Just rearrange it a little bit, okay? So now I have force, I'm putting it as a function of time, times acceleration as a function of time, plus m times velocity as a function of time times jerk as a function of time, okay? And that is how we would calculate the power surge, okay? If you didn't have a function for power, this is how you would do it. What would you have to have a function of to get this? What would you have to have? Well, you would have to have force as it varies with time, right? And you would have to have x as it varies with time. Those are the only two things you would need to do this. Oops. The only two things, erase that, you would need. You need these two expressions right there. Why do you only need x with respect to time? Because I can get velocity from this, I can get acceleration from that, and I can also get the jerk from that. As long as you have position, you can get all of these, okay? But you would also need force as it relates to time, and that's a completely separate function, okay? Adding those two terms together gets you the power surge, okay? So hopefully this video has given you a little bit of intuition on how to deal with moving around differentials, differentiating both sides of an equation, integrating all that stuff to get all the stuff that you've seen before in physics, but we're going to be doing a lot of this in thermodynamics and kinetics quite a bit, all throughout PChem and other branches of physics. So in the next video, we're actually going to do the same thing, but with Coulomb's law, because later on in quantum mechanics, you are going to be dealing with Coulomb's law. And there's a lot of formulas you need to memorize, and if you can actually derive them on the spot, which actually is not that difficult. It's very easy to know exactly what to do if you just start with Coulomb's law. So make sure to like the video, subscribe to the channel, and thank you for watching. See you in the next video where we do more transforms.